Hi, I'm Dave Weens with Mentor, a Siemens Business. This webinar is the first in a series aimed at optimizing verification throughout the electronic systems design process to ensure on-time, high-quality product releases. In this short introduction, I'll first look at a few challenges impacting design teams, then cover best practices in the industry for in-design validation, as well as the results you should expect. To start, let's discuss some typical challenges. Research by Lifecycle Insights showed that only 25% of design projects came out on time without applying extra resources. 58% missed their dates or robbed resources from other projects to try to come in on time. Given that time to market is often a key driver, this shows that project health overall across the industry is relatively poor. In addition, a major source of delays and cost overruns is design respins. This same research looked at redesigns forced when errors were found in physical prototypes or production boards. You can see the time and cost breakdown per spin on the left. And I'd note that these are averages. For high performance or advanced manufacturing boards, the cost can be much higher. The chart on the right just puts it in perspective across multiple projects. This is cost and time that is currently baked into existing schedule projections because it's somewhat expected that designs will go through 2 to 3 respins. This is really unreasonable and unnecessary, and it only gets worse because with added product complexity come problems never seen before, increasing the potential for even more respins as teams hunt in the dark for the root cause of problems. Speaking of increased product complexity, the number of things the engineering team needs to design for, like performance, cost, time, and manufacturability, are a key challenge to consider, even forcing trade-offs between requirements in some cases. Some of these product complexities may look familiar to you. Increased signal speeds, function density, manufacturing yield, power and heat management, the list goes on. Any of these could be the cause of increased respins in your engineering team. The first thing that typically happens when an engineering team faces a new challenge is that a domain specialist is brought in or trained to identify the problem. The specialist is then used as the reviewer of last resort before designs go to manufacturing. This is certainly a step in the right direction. Some problems will be found sooner. But from a process perspective, a bottleneck is created as multiple engineers submit their designs for review. And because the design engineers don't have the same specialized domain training, their work is more likely to go through multiple virtual respins before the design is approved. This adds delay to the schedule, and in some cases still lets errors through, as stressed specialists try to keep up with the workload. Speaking of virtual respins, there's an inherent cost in the form of process delays. This is also somewhat hidden in the average schedule projection. Cost can be represented in incremental development time, additional resources, or even lost time to market. The absence of a strategy to detect and resolve errors early in the development phase can have a major profitability impact. In this research from ResearchGate, in yellow you can see a traditional model showing the increasing cost of errors for system-level test as a design progresses. The same holds true during design, where errors sent back from specialists create iterations that exponentially grow in cost as the length of time increases between when the problem was introduced and when it's found. And since upwards of 70% of a product's cost are committed early in design, design errors can have a significant impact on the end product cost. Errors need to be found as early as possible to mitigate risk. I think I've made the point. 3 respins is not best practice. And with specialists focused on only a few critical issues, everything else is left to manual, time-consuming peer reviews that often miss errors. Fortunately, there's a better way. Here are a set of 3 interrelated best practices deployed by industry-leading engineering teams. First, verification, whether manual or automatic, should happen throughout the design process, not just at the end. Second, by automating design reviews, the coverage is higher and more problems are found sooner. And third, by doing automated verification throughout design by design authors, the specialists are out of the critical path and able to focus on more critical second-order problems. Let's take a bit deeper look at each of these best practices. As I noted earlier, verification has slowly moved left in the design process. First, verification was done at manufacturing and test, shown at the right side of the traditional flow in blue. Then it moved earlier to sign off an NPI. So it's only logical to continue that progression left by integrating verification throughout the design process. This is a true digitalization strategy, with verification accuracy improved through flow integration, creating a high-quality digital twin model. In yellow, you see a sample of the types of verification that could and should be happening at each stage of the flow. Some you might expect, like AMS simulation associated with schematic design. Others, like DFT, have moved all the way from the end of the process to the beginning, where engineers make decisions that have a direct impact on testability. The key here is to integrate verification at the stage where errors are introduced in the first place, so they can be found quickly and fixed by the design author directly working on that stage. In addition, because of the pervasive multidiscipline technologies that can be integrated within a design environment, trade-off analysis, for instance, power versus thermal considerations or performance versus manufacturability, can be undertaken early to enable product optimization. The goal of this process is first pass or zero spin success of higher quality, lower cost products. I realize that this process looks more complex than the typical flow, but the addition of extra verification steps is directly offset by fewer spins and lower risk, often resulting in reduced design times. The process on the left reflects a traditional approach where design teams review each other's work. As noted earlier, these are often manual, requiring a peer to quickly try to understand the design's intent and scan for possible errors. This process forces the primary engineer to stop working on the design, take their peers away from the designs they were working on, and spend lots of time in group meetings. And as you might expect in this inefficient process, they still miss things. Automation of these reviews enables the primary engineer to perform reviews in real time as the design progresses, without distracting their peers. Automation also ensures that all engineers are using the same best practice process and delivers higher coverage than the manual peer review process. This last stage really pulls the other two together. The specialist is utilized early on to define the processes for automated reviews. This might include tool and model setup, constraints to check, and types of checks to be run at each stage. There could be multiple specialists deployed in a process like this. For instance, ones for signal integrity, for thermomechanical, or manufacturability. The engineering teams perform their own design reviews, then pass to the specialist who can focus on just the second-order critical problems the engineers can't fix, rather than focusing on reviewing the entire design. The net result is faster throughput of higher quality designs. An Aberdeen survey asked about processes for design verification. It classified the use of simulation by design engineers early in the design process as best in class for the following reasons. First, it enabled product innovation and optimization because physical prototypes were reduced 27% through the use of virtual prototypes and virtual testing. This allowed them to explore hundreds of design iterations, freeing them up to identify and focus on designs with the highest potential. It also improved time to market. Best-in-class designers improved their length of development time by 29%, 6 times the rate of improvement by all others. Best-in-class organizations also met their time to market targets 76% of the time, a 17% higher rate than all others. It also reduced product costs. 71% of best-in-class designers met their product cost targets. And higher product quality was also achieved. 77% of best-in-class firms met their product quality targets. Plus, best-in-class products were more likely to work right the first time and less likely to require rework, as the best-in-class improved their ECOs after release to manufacturing by 21%. I've got a couple examples of engineering teams that have adopted the best practice methodologies. Delphi is a great example of an organization that embraced the shift-left practice for signal and power integrity. By deploying validation tools early in the process, they enabled design engineers to run their own analysis, resulting in an 80% reduction in engineering effort and time to sign off. Keysight faced costly, latent design errors causing multiple respins. They've now deployed manufacturability verification technology within the layout process to accelerate design cycles and improve product quality. Hopefully, I've made the point through multiple examples that a best practice validation strategy reduces time and cost and improves product reliability. Cost and time are saved by finding problems early in design, minimizing design iterations and manufacturing respins. Improved validation tool integration and ease of use enable non-specialists to run checks, reducing the specialist bottleneck. Tool automation eliminates the need for manual reviews and minimizes physical tests in the lab. Given the ability to evaluate alternatives, the cost of the overall system can be greatly reduced. On the reliability side, 100% coverage of designs greatly reduces the chances of catastrophic errors slipping through the cracks. It also reduces the noise of false errors often introduced by the physical testing process itself. By enabling early analysis by non-specialists, the specialists are freed to focus on just the critical issues and also look for product optimizing alternatives. And finally, by optimizing the performance margins of a design through analysis, the rate of field failures will drop. By now, I'm sure you noticed the green button with related resources at the bottom of your screen. These papers, noted on the left here, offer further depth behind the research that I highlighted. This is the first in a series focused on optimized design and verification methodologies. You can see the set on the right. These are engineer focused and will provide design education and use cases to put the methodologies I've discussed into practice. Thanks for attending this session. If you're interested in further information on these best practices and enabling technologies, please attend the follow-up events or contact your local sales representative.